When we look out into the depths of space, we are also looking into a universe that is slowly changing with time. Stars are born and disappear, galaxies drift apart, and the cosmos never truly stands still. But how do we measure time when the universe itself is the clock? Can something so vast ever truly grow old? Tonight, we gently explore the hidden rhythm of cosmic time, the quiet force guiding the life of the universe. Where did it all begin? For us, the story of the universe is not merely a chain of events that took place in some distant past. It is a living narrative, unfolding before our eyes, echoing in the stars, resonating in the very fabric of space-time. The vastness of the universe is often overwhelming. It seems endless, as though it will always exist in its present form. Yet, in its heart, a profound transformation is taking place. The universe is aging. What we see as a boundless cosmos, in fact, had a beginning, a singular moment when everything we know and all that we don't came into existence. A singularity, a point of infinite density, where space and time as we know them were born. This moment, this singularity, marks the birth of everything from the stars that light our skies to the molecules that make up life. It is called the Big Bang. It's easy to think of the Big Bang as an explosion, but it wasn't like any explosion we're used to. It wasn't a burst in the center of space. Rather, it was the very stretching of space itself. Imagine a balloon being inflated. At first, it's tiny, but as the air expands, the balloon gets bigger and bigger, with every point on its surface moving away from each other. Now, picture that balloon as the fabric of space itself, and what was once a singularity, an infinitesimally small point, began to stretch and expand, creating everything that we now see around us. We call this process cosmic inflation. In those first few moments, the universe expanded faster than the speed of light. That's right, faster than light. And before the blink of an eye, the cosmos was already on its way to becoming the vast, intricate expanse we witness today. The incredible part, this expansion didn't break any laws of physics. According to Einstein's theory of relativity, nothing can travel faster than light. However, that only applies to objects moving through space. Space itself, well, space can stretch as much as it wants. It's no longer bound by the same rules. This extraordinary event, the Big Bang, wasn't just some random burst. It was a profound shift that began the cycle of everything matter, energy, galaxies, and even time. As the universe stretched out, it cooled down. From that cooling came the formation of the first atoms, hydrogen and helium. These simple building blocks of matter would go on to create everything we know and love in the universe. Over time, matter began to coalesce, giving birth to stars, which in turn formed galaxies, and eventually us. Our story begins, as all stories do, in a moment of incredible change. And this moment, this Big Bang, is what set the stage for everything we've ever known. But how do we know that the Big Bang truly happened? The universe doesn't tell its secrets freely. For centuries, humans looked up at the stars, wondering about the origins of all that they could see. It wasn't until the early 20th century that scientists began to put the pieces together. It was Edwin Hubble, in the 1,920 seconds, who first discovered that galaxies were moving away from us. This simple observation was more than just an interesting fact about the universe. It was proof that space itself was expanding. This discovery gave us the first crucial clue that the universe had a beginning. If galaxies are moving apart, it means they must have once been closer together, possibly at a single point in time. Further evidence for this idea came from the discovery of the cosmic microwave background, CMB, a faint glow permeating the entire universe, left over from the very first moments after the Big Bang. It is the afterglow of the universe's creation. still traveling through space after nearly 14 billion years. This faint whisper of light from the past is what solidified the idea of the Big Bang. It is not just a theory, it is an observation, a fact encoded in the very fabric of the cosmos. In the decades since, scientists have used more advanced instruments to probe deeper into the universe's history. The Planck satellite, launched by the European Space Agency, took meticulous measurements of the CMB, providing us with detailed maps of the universe's infancy. These observations have enabled scientists to refine our understanding of the universe's age, and today, with remarkable precision, we know the universe is about 8 billion years old. But how do we measure something so vast, so distant, so old? It's no simple task. Our best tool for measuring the universe's age is the study of light. Light, after all, travels at a fixed speed. So when we look at distant stars or galaxies, we are essentially looking back in time. The farther away an object is, the older the light we're seeing. By measuring the light from ancient stars and galaxies, scientists can calculate how far back in time they are looking, and through this method, they can determine the age of the universe with incredible accuracy. One of the most groundbreaking advancements in recent years has been the James Webb Space Telescope JWST. With its ability to peer deeper into space than any telescope before it, JWST is helping scientists see the very first galaxies that formed after the Big Bang. By studying these early galaxies, we can trace the universe's evolution and gain insights into how it has aged over billions of years. Yet, even with all our advances, there remains much we don't know. The universe continues to surprise us, challenging our understanding at every turn. And perhaps that's the most intriguing part of this story. The more we learn, the more we realize just how much we don't know. But that's the beauty of it, isn't it? The mystery, the wonder, the infinite potential for discovery. As we look to the stars, to the galaxies far away, and to the very fabric of time itself, we are reminded that the universe is not just something we study, it is something we are part of. We are, in a sense, the universe becoming aware of itself. We are its story, unfolding, one moment at a time. And so, as we stand on the shoulders of those who came before us, exploring the universe's beginnings, we must remember that our story is still unfolding. Time is not just a measure, it is the very essence of our existence. And the universe, ever aging, ever expanding, will continue to guide us, one discovery at a time. As we venture further into the vast expanse of the cosmos, we come face to face with one of the most extraordinary phenomena of our universe, the expansion. The universe, as we know it, is not a static entity. It is in a constant state of flux, expanding, stretching, and evolving. But how did we come to understand this truth? And what does it mean for us? For centuries, we believed that the universe was static, that it had always been the same. Ancient philosophers, like Aristotle, believed that the heavens were unchanging, eternal. This belief persisted for millennia, until a breakthrough in the early 20th century turned this notion on its head. The first clues about the expanding universe came from the work of Edwin Hubble in the 1920 seconds. Hubble, working with the powerful telescopes of his time, discovered that galaxies were not only moving away from us, but were doing so at a rate proportional to their distance. This phenomenon is known as redshift, a shift in the wavelength of light toward the red end of the spectrum, which occurs when objects move away from the observer. At the time, this discovery was nothing short of revolutionary. Hubble's observations revealed that the fabric of space itself was stretching, pulling galaxies apart. This was an unmistakable sign that the universe had a beginning, a moment when all matter, energy, and space were compacted into a singular point. the singularity that birthed the Big Bang. Hubble's discovery led to the formulation of the Hubble law, which describes how galaxies move away from each other with a speed that is directly proportional to their distance. It was a concept that would forever alter our understanding of the universe. The more distant a galaxy is, the faster it moves away from us. This observation gave rise to the idea that the universe is not only expanding, but that it has been expanding since its very inception. But the story does not end there. If the universe is expanding, how far does it stretch? And where does it end? These are the questions that have puzzled scientists for decades, and while we don't have all the answers, we do have powerful tools at our disposal to help us answer them. One such tool is the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang itself. The CMB provides a snapshot of the universe just 380,000 years after its birth, giving scientists a glimpse into its early stages. By studying the CMB, scientists can determine not only the age of the universe, but also its rate of expansion. The CMB has also provided us with important clues about the composition of the universe. While we see the familiar galaxies, stars, and planets, they make up only a small fraction of what exists in the cosmos. The rest is made up of invisible substances, dark matter, and dark energy. These mysterious forces are essential to the expansion of the universe, yet we still don't fully understand what they are. To understand the universe's expansion, we must first address these invisible forces. Dark matter, which makes up about 27% of the universe, is a form of matter that cannot be seen directly but is inferred from its gravitational effects on visible matter. It is the glue that holds galaxies and galaxy clusters together, preventing them from flying apart as they expand. Then there's dark energy, a force that accounts for roughly 68% of the universe. Dark energy is responsible for the accelerated expansion of the universe. It works in opposition to gravity, pushing galaxies apart rather than pulling them together. This mysterious energy was first observed in the late 1990 seconds when scientists studying distant supernovae discovered that the universe's expansion was speeding up instead of slowing down. As was previously expected, the discovery of dark energy was a profound moment in the history of cosmology, as it suggested that the fate of the universe is tied to forces that are entirely invisible and currently beyond our comprehension. These two forces, dark matter and dark energy, are the driving factors behind the universe's expansion. They shape the cosmos, yet they remain largely unseen, hidden in the depths of space, only detectable through their influence on the visible universe. The existence of dark matter and dark energy raises some intriguing questions about the future of the universe. If dark energy continues to push the universe apart, will it expand forever, or will there be a moment when the expansion slows down, reverses, and the universe begins to collapse in on itself? We simply don't know yet. But this uncertainty is what makes the study of the universe so exhilarating. Each discovery leads to more questions, more mysteries to unravel. In our quest to understand the expanding universe, we are now on the brink of a new era of discovery. The James Webb Space Telescope, JWST, launched in December 2021, is designed to peer further into space than ever before. With its ability to observe the universe in infrared, JWST can look past the cosmic dust that often obscures our view and capture the light from the very first galaxies that formed after the Big Bang. JWST is helping us study distant galaxies and their role in the universe's expansion. By examining these early galaxies, we can learn more about how the universe evolved over time and what forces have shaped its growth. This groundbreaking telescope is poised to answer many of the questions that have haunted scientists for centuries, including the true nature of dark matter, dark energy, and the mechanics of cosmic inflation. As we look to the stars and galaxies through the lens of JWST, we are witnessing the unfolding of a story that has been billions of years in the making. The light we see today is not just a snapshot of the present, It is a window into the past, a glimpse into a time long gone. The expansion of the universe is a cosmic symphony, with each galaxy and star playing its part in an ever-evolving dance. And as we continue to study the universe's expansion, we come closer to understanding our place within this vast, interconnected web of time and space. The universe is alive, and its story is still unfolding, an infinite journey that will continue to captivate and inspire us for millennia to come. As we move through the stretches of space, we are reminded of how small we are, and yet how profoundly connected we are to the vast cosmos. We are not merely observers of the universe, we are a part of it, woven into the very fabric of time and space. And as the universe continues to expand, so too does our understanding, taking us on a journey that stretches far beyond the horizon of what we can see and into the infinite possibilities of what we have yet to discover. The journey of exploration never ends, and the universe, in all its glory, continues to unfold before us. When we look up at the night sky, we often see only the familiar twinkling of stars scattered across the vastness of space. However, these stars are not mere distant points of light. They are the very architects of the universe's chemical makeup and the life force that powers the cosmos. Stars are not static. They are the result of dynamic and powerful processes that shape the fabric of the universe. At the heart of star formation lies the process that begins in the cold. Dense clouds of gas and dust scattered throughout the cosmos. These clouds, known as molecular clouds, are the birthplaces of stars, though they begin as dark, unassuming regions. These clouds are made primarily of hydrogen, the simplest element in the universe, but also contain helium, carbon, oxygen, and heavier elements. Within these immense clouds, the material is cool and diffused and seemingly inert, yet it holds within it the seeds of creation. When a disturbance, such as a nearby supernova explosion or the passing of a galaxy, shakes one of these molecular clouds, it causes the gas and dust particles within to collapse under their own gravity. As the particles move inward, the cloud becomes denser, and the pressure increases. With each passing moment, the cloud becomes a furnace, heating up as it condenses, eventually reaching temperatures and pressures high enough to ignite nuclear fusion, the process that powers stars. Before reaching this critical point, the collapsing material forms what is known as a protostar, a dense, hot ball of gas at the center of the collapsing cloud. It is in this phase that a star begins its long and often tumultuous journey toward full maturity. In this embryonic stage, the protostar emits intense radiation, and the surrounding gas and dust are blasted away, leaving behind a young, growing star. The exact path a star will follow depends heavily on its mass. Stars come in all sizes, from the faintest red dwarfs to the most massive supergiants. The mass of a star determines how long it will live, how hot it will burn, and what its final fate will be. Stars that are born with a mass similar to or smaller than our Sun will have long, stable lifetimes, providing the perfect conditions for life to arise on nearby planets. On the other hand, stars that are much more massive burn through their fuel much faster, living shorter, more explosive lives. These stars are the heavyweights of the universe, capable of producing elements much heavier than hydrogen and helium through the process of nuclear fusion. The birth of a star is a truly awe-inspiring process. The forces at work during the collapse of a molecular cloud are staggering, and the eventual outcome is nothing short of magnificent. Stars are, after all, the engines of creation. Through their intense heat and pressure, they forge the heavier elements that make up everything around us: iron, calcium, oxygen, and even the carbon in our bodies were all once forged in the hearts of stars. slowly released into the cosmos through a variety of explosive processes. Not all stars are created equal. Their lifespans, their roles in the universe, and the elements they create are dictated by their mass and the conditions they encounter. While some stars burn brightly for billions of years, others have explosive and brief existences, creating much of the matter that forms planets and galaxies. Stars are often classified into several categories based on their mass. Red dwarfs, for example, are small, cool stars with less than half the mass of our Sun. Despite their modest size, red dwarfs have remarkably long lives, burning their fuel at a slow rate. These stars can burn for up to 100 billion years, far longer than the current age of the universe. As a result, no red dwarfs have yet exhausted their fuel and exploded. They are the slow, steady workers of the universe. Yellow dwarfs, like our Sun, have a middle-of-the-road mass and life expectancy. They burn their hydrogen fuel at a more moderate pace, allowing them to shine for about 10 billion years. During their lifetime, these stars provide the ideal conditions for life to develop on planets orbiting them, as they emit a steady, life-sustaining stream of radiation. When a star like our Sun runs out of hydrogen in its core, it will begin to burn helium, and the star will expand into a red giant. In this phase, it will swallow up nearby planets and undergo dramatic changes before finally shedding its outer layers and leaving behind a dense, hot core, a white dwarf. On the opposite end of the spectrum are the massive stars, those that are several times more massive than the Sun. These stars are powerhouses, burning through their fuel much faster than their smaller counterparts. As a result, their lifetimes are much shorter, often just a few million years. When these massive stars reach the end of their lives, they collapse under their own gravity, triggering a supernova explosion that can briefly outshine an entire galaxy. The remnants of the explosion can form neutron stars or even collapse into a black hole, objects with gravity so strong that not even light can escape. The diversity of stars, their varying sizes and life paths, is what makes the universe such a fascinating place. Stars are not merely burning balls of gas, they are chemical factories, each playing a vital role in the creation of the elements that make up the world around us. Stars are far more than just shining lights in the sky. They are the factories where elements are born. The process of stellar nucleosynthesis refers to the creation of new elements in the cores of stars through nuclear fusion. In the early stages of a star's life, hydrogen is fused into helium. But as the star ages and the pressure in its core increases, it begins to fuse heavier elements. For stars like our Sun, once the hydrogen in the core runs out, the star will begin to fuse helium into heavier elements like carbon and oxygen. As the star continues to burn through its fuel, it can produce even heavier elements, such as neon, magnesium, and silicon. The process of nuclear fusion in stars is the ultimate source of the elements that make up the planets, the air we breathe, and the very atoms that compose our bodies. However, the most dramatic element formation occurs during the explosive death throes of massive stars. In their final moments, these stars fuse elements all the way up to iron, the most stable element. When the core reaches iron, fusion can no longer generate enough energy to counteract the force of gravity, and the star collapses in a violent explosion. This supernova not only releases an enormous amount of energy, but also creates the heaviest elements in the universe, including gold, platinum, and uranium. These elements are then scattered throughout space, enriching the interstellar medium and providing the building blocks for future generations of stars, planets, and life. In this way, the death of one star provides the raw materials for the next generation. The cycle of stellar birth, death, and rebirth is the engine of cosmic evolution. And it is through this process that the universe continues to evolve, creating the conditions necessary for the formation of planets and life. As we watch the stars twinkle in the night sky, we are witnessing the aftermath of billions of years of cosmic creation. We are seeing the remnants of long-dead stars, and in some cases, we are even watching new stars being born. The life cycle of stars is a testament to the power of cosmic forces and the ongoing dance of creation and destruction that shapes the universe. The story of star formation is not just a scientific tale. It is a story of wonder and awe, of the forces that shape the very fabric of reality itself. It is a reminder that the universe is alive, constantly evolving, and always changing. And it is through the stars, these incredible, fiery furnaces of creation, that we are able to trace the very origins of the elements that make up everything we know. The life of a star is a constant struggle between two forces: gravity, which wants to collapse the star inward, and the pressure from nuclear fusion, which pushes outward. This cosmic battle shapes every stage of a star's life, determining its fate and its ultimate demise. Stars begin their lives as gas and dust, coming together under the influence of gravity. But once a star reaches a critical mass, it enters a phase of nuclear fusion, where lighter elements like hydrogen are fused into heavier elements like helium, releasing vast amounts of energy. This energy creates an outward pressure that resists the inward pull of gravity, allowing the star to remain stable for millions or even billions of years. But this balance does not last forever. As the star consumes its hydrogen fuel, it eventually runs out of the material that powers nuclear fusion. When that happens, the core of the star contracts under gravity, while the outer layers expand and cool. This marks the transition from a main sequence star to a red giant, the next phase of its life. During this red giant phase, the star begins to fuse heavier elements like helium into carbon and oxygen. The core of the star continues to shrink and heat up, while the outer layers expand dramatically. For stars like our Sun, this phase will last for about 1 billion years before they begin to shed their outer layers in a dramatic display of energy. This creates what is known as a planetary nebula, a vast cloud of gas and dust that surrounds the remaining core. The fate of a star after the red giant phase depends on its mass. Stars with less than about 8 times the mass of our Sun will end their lives as white dwarfs, dense remnants that no longer undergo fusion. Over billions of years, these white dwarfs will cool and fade into black dwarfs, objects that are virtually invisible. Yet their mass remains a testament to the star that once existed. On the other hand, stars with greater mass will undergo a more violent end. When the core of these massive stars runs out of fuel, the star will collapse under its own gravity, triggering a supernova explosion. This cataclysmic event releases an incredible amount of energy, briefly outshining an entire galaxy. The core of the star, if it is massive enough, will collapse into a neutron star, or, in the case of the most massive stars, a black hole, an object so dense that not even light can escape its gravitational pull. The process of stellar death is not just an end, but a transformation. The explosion of a supernova is one of the most energetic events in the universe, scattering elements like carbon, oxygen, and iron into space. These elements are the building blocks for new stars, planets, and even life. In this way, the death of a star is a necessary part of the cycle of creation that sustains the universe. Stars are not just created and destroyed, they recycle. The elements that are forged in their cores during the process of nuclear fusion are scattered into the surrounding space when they die, enriching the interstellar medium with the raw materials for future generations of stars and planets. This ongoing cycle of stellar birth, death, and rebirth is what keeps the universe dynamic and ever-changing, providing the conditions for new worlds to form. For us, living on one such planet, The death of stars is more than just a cosmic event. It is the very reason we exist. Without the heavy elements produced in stars, there would be no planets, no water, and no life. Our existence is a direct consequence of the life and death of stars. A reminder that we are part of an ancient and ongoing process that stretches back to the earliest moments of the universe. As we look up at the stars, we are not only witnessing the light from stars that have long since passed, we are also gazing at the legacy of the stars that came before, the very elements that allow life to flourish on Earth. The life cycle of stars is not just a scientific concept, it is a story of creation, destruction, and rebirth, woven into the fabric of the universe itself. The cosmic dance of stellar evolution, from the birth of a star to its eventual death, is one of the most profound and awe-inspiring aspects of the universe. It is a process that reminds us of the interconnectedness of all things and our place within this vast and ever-evolving cosmos. Through the lives and deaths of stars, the universe continues to create, to evolve, and to bring forth new possibilities. The beauty of this process lies in its cycles, the endless birth and rebirth, the creation and destruction, the continuous reshaping of the universe. It is a story that has been unfolding for billions of years and will continue for billions more. And as we continue to study the stars and learn more about their life cycles, we can gain a deeper understanding of our own place in the grand tapestry of the cosmos. Every star we see in the night sky is a reminder of the incredible forces at work in the universe, forces that have shaped the very elements of life itself. And as we look to the future, we can only marvel at the ongoing process of star formation, the cycle of life and death that is central to the universe's evolution. Galaxies, those magnificent cosmic islands scattered across the vast expanse of the universe, are not static. They are living, evolving entities, shaped by the forces of gravity, dark matter, and the influence of supermassive black holes. The transformation of galaxies is a dynamic process that spans billions of years, a story written in the stars and dust that makes up these vast structures. At the core of every galaxy, including our own Milky Way, lies a supermassive black hole, a beast of gravity so powerful that not even light can escape. These black holes are not only the most mysterious and enigmatic objects in the universe, they play a fundamental role in shaping the galaxies around them. Their gravitational pull influences the orbits of stars, gas, and dust. But they also have a deeper, more complex relationship with their host galaxies. When galaxies collide, it is not just a crash of stars, which, due to the vast distances between them, are unlikely to collide directly, but a clash of cosmic structures, of gravitational forces, of energy. The process is slow but inevitable, as galaxies can be drawn together over millions or even billions of years. During these collisions, the black holes at the centers of the merging galaxies begin to interact with one another. The gas and dust that swirl around the black holes begin to spiral inward, and as they do, they heat up, releasing incredible amounts of energy in the form of radiation. These collisions often trigger a burst of star formation, called a starburst, where new stars are born at a staggering rate. The energy released in this process is enough to alter the structure of the galaxy itself. Some stars are ejected into space, while others are pulled into the heart of the merging galaxies, increasing the mass of the central black hole. Over time, this starburst subsides, and the galaxies continue to evolve, sometimes forming a new, larger galaxy from the remnants of the original colliding galaxies. While this process of galactic collision and fusion is one of the most dramatic ways galaxies change, it is not the only way. Over time, galaxies also evolve through the slow accumulation of matter from their surroundings. The gravitational influence of nearby galaxies, or the dark matter that permeates space, can draw in gas, stars, and dust, gradually adding to a galaxy's mass and size. The types of galaxies that emerge from these processes are varied. There are spiral galaxies, like our Milky Way, which feature arms of stars and gas swirling out from a dense central bulge. These galaxies continue to form new stars in their arms, a process that can go on for billions of years. The spiral shape of these galaxies is the result of the balance between the rotation of the galaxy and the pull of gravity at the center. But not all galaxies are so graceful. Some galaxies take on the shape of an elliptical galaxy, a more spherical or oval shape, often created by the merger of two or more spiral galaxies. Elliptical galaxies, unlike their spiral cousins, have little to no interstellar gas and dust left. They are home to older stars that have already exhausted the fuel for new star formation. These galaxies are often the result of galactic collisions that have stripped away the gas and disrupted the structure of the galaxies involved. As a result, elliptical galaxies are often described as dead galaxies, their star formation activities having slowed or ceased entirely. On the other end of the spectrum are irregular galaxies, which do not follow a defined shape or pattern. These galaxies are often in the midst of formation or are undergoing significant disruption due to the gravitational forces of neighboring galaxies. Irregular galaxies are often small and chaotic, their stars scattered unevenly, with no central bulge or spiral arms. Despite their lack of order, these galaxies can still be sites of vigorous star formation, and they are crucial to our understanding of the early universe, as many of them resemble the early galaxies that existed shortly after the Big Bang. The interplay between galaxies is not just a story of collisions and mergers, it is also a story of dark matter. This invisible substance makes up about 27% of the universe and plays a critical role in galaxy formation. Dark matter acts as a gravitational scaffold, helping to hold galaxies together and influencing their overall shape. While we cannot see dark matter directly, its presence can be inferred from the way galaxies move and interact. Without dark matter, galaxies would likely fly apart, unable to hold themselves together under the influence of gravity. At the heart of many galaxies lies the supermassive black hole. These enigmatic objects can be millions or even billions of times the mass of our Sun. Their gravitational influence is so powerful that it affects not only the stars and gas within the galaxy, but also the galaxy's evolution itself. As gas and dust spiral into these black holes, they create powerful jets of radiation that can blow away the surrounding material, shutting down star formation in the galaxy's core. In some cases, these supermassive black holes can even power active galactic nuclei, AGN, regions of intense radiation that outshine the rest of the galaxy combined. The energy released by an AGN can alter the surrounding environment, affecting the development of new stars and the overall shape of the galaxy. Over time, as galaxies merge and evolve, their central black holes grow larger and more powerful, shaping the galaxies in ways that are only beginning to be understood. The story of galaxy evolution is far from over. As the universe continues to expand and galaxies continue to interact, new structures will form, new stars will be born, and new supermassive black holes will emerge. In the distant future, it is predicted that our own Milky Way will collide with the Andromeda Galaxy, leading to the creation of a new, massive elliptical galaxy. This collision, while billions of years away, will mark a new chapter in the history of our galaxy, a chapter that will shape the fate of countless stars and planets. Yet, the universe's expansion continues to outpace the force of gravity, and as galaxies move further apart, the future of these cosmic giants becomes uncertain. Over the course of trillions of years, galaxies will eventually be isolated from one another, leaving behind a void of dark matter and faint starlight. The universe, once filled with the brilliance of countless stars and galaxies, will gradually fade into an endless, silent night. The evolution of galaxies is an ongoing process, a cosmic dance that has been happening for billions of years and will continue for billions more. Each galaxy, from the smallest irregular galaxy to the largest elliptical behemoth, carries with it the story of the universe itself, a story of creation, destruction, and rebirth, written in the stars. As we look up at the night sky, we are witnessing the legacy of this process, a reminder that the universe is alive, always changing, always evolving, and always, in some way, becoming something new. The galaxies, with all their complexity and beauty, remind us of the forces at work in the universe. They are a testament to the power of gravity, the influence of dark matter, and the enduring mystery of black holes. Their lives, just like the stars within them, are a reflection of the larger processes at play in the cosmos. And as we continue to explore these vast structures, we can only begin to imagine the future of galaxies, as they continue to shape the universe and, ultimately, our understanding of it. Galaxies are not static, they are dynamic systems, continuously evolving, shaped by an intricate web of cosmic forces. From their formation to their ultimate fate, galaxies undergo profound transformations. Their size, structure, and composition change over billions of years, driven by interactions within themselves and with other galaxies. Galaxies are not isolated, fixed islands in space. They are living, breathing entities, constantly in motion. This process of evolution begins long before the first stars light up their cores, and it continues as each galaxy grows, interacts, and merges with others in an ever-changing cosmic dance. In the early universe, the seeds of galaxies were sown by dark matter. This mysterious substance, which makes up about 27% of the universe's mass, interacts gravitationally but not electromagnetically, meaning it doesn't emit or absorb light. The presence of dark matter in the early universe formed dense regions, known as dark matter halos, that acted as the scaffolding for the galaxies to grow. As regular matter, made up of hydrogen, helium, and dust, fell into these halos, the first stars began to form. These early stars were the first generation, often massive and short-lived, leaving behind heavier elements necessary for later star formation. The process of galaxy formation continued as gravity drew the gas and dust together, causing it to collapse into larger structures. The galaxies that emerged were not uniform. Some formed as spiral galaxies, with flat, disc-like structures and prominent spiral arms that contain regions of active star formation. These galaxies have a central bulge, a dense area populated by older stars, and spiral arms that are often sites of young blue stars. Our Milky Way is a prime example of a spiral galaxy, one of the most common types in the universe. However, not all galaxies take on this beautiful spiral shape. Some form as elliptical galaxies, which are more spheroidal in shape and composed primarily of older, redder stars. These galaxies typically have little to no gas or dust, making them poor environments for new stars to form. They are often the result of mergers between smaller galaxies, which disrupts their spiral structure and strips away the gas needed for star formation. Over time, the elliptical galaxies grow older and dimmer, their star formation coming to a near halt. Another type of galaxy, called irregular galaxies, lacks the clear structure seen in spiral and elliptical galaxies. These galaxies are often smaller, more chaotic, and form due to gravitational interactions with other galaxies. As galaxies collide, the structure can become distorted, leading to irregular shapes. Despite their lack of symmetry, irregular galaxies are still active sites of star formation, often filled with clouds of gas and dust. Galaxies are rarely solitary. They interact with one another over time, their gravitational forces pulling them together, leading to collisions and mergers. These interactions are not immediate, but rather unfold over millions or billions of years, sometimes resulting in the complete transformation of the galaxies involved. When two galaxies collide, they don't typically crash into each other with the same force as two solid objects would. The vast distances between stars within each galaxy make direct collisions between stars improbable. However, the gas and dust clouds within the galaxies are dense enough to interact, leading to shock waves and the compression of material. These interactions often trigger bursts of star formation, known as starbursts. These violent events occur when the gas clouds in the galaxies collide and compress, creating the perfect conditions for new stars to form at an accelerated rate. During these starbursts, the rate of star formation can be up to 10 times greater than normal. As the collision progresses, the gravitational forces involved begin to change the structure of the galaxies. The spiral arms of a spiral galaxy may be stretched and distorted, and the galaxy may lose its beautiful, regular shape, often transforming into an elliptical galaxy. This merging process often leads to the formation of a supermassive black hole at the center of the newly formed galaxy, as the matter from both galaxies is funneled toward the center, creating an intense gravitational pull. At the center of most large galaxies lies a supermassive black hole, a monster of gravity that can be millions or even billions of times the mass of our Sun. These black holes are not just passive objects, they are deeply intertwined with the galaxies in which they reside. They influence the orbits of stars, regulate the rate of star formation, and play a significant role in the overall evolution of the galaxy. As galaxies merge, their supermassive black holes can also collide and eventually merge, releasing enormous amounts of energy in the form of gravitational waves. These waves, predicted by Einstein's theory of general relativity, were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. These observations confirmed the violent nature of galactic mergers and the profound impact supermassive black holes have on the galaxies they inhabit. The influence of a supermassive black hole extends beyond the boundaries of the galaxy. As matter falls into the black hole, it forms an accretion disk, which can emit powerful radiation. This process can generate jets of high-energy particles, which are shot out from the poles of the black hole at nearly the speed of light. These jets can have profound effects on the surrounding galaxy, heating gas and preventing it from collapsing to form new stars. This feedback mechanism is essential for regulating star formation and determining the ultimate fate of the galaxy. While the visible matter in galaxies, such as stars and gas, is crucial to their structure, the majority of a galaxy's mass comes from dark matter. Dark matter does not emit light, so it is invisible to our current telescopes, but its presence can be inferred through its gravitational effects on the motion of galaxies and clusters of galaxies. Dark matter forms the cosmic web, a vast network of filaments that stretches across the universe, guiding the formation and evolution of galaxies. These filaments of dark matter act as a scaffold, providing the necessary gravitational pull for galaxies to form and grow. Without dark matter, galaxies would not have enough mass to remain gravitationally bound. The study of galaxy clusters has revealed that dark matter plays a crucial role in shaping the distribution of galaxies, with dark matter halos providing the gravitational well in which galaxies sit. Over time, the interaction between dark matter and visible matter has shaped galaxies in profound ways. The distribution of dark matter in and around galaxies is not uniform, and its density decreases at greater distances from the galaxy center. This results in galaxies being surrounded by a large halo of dark matter, which extends far beyond the visible edges of the galaxy. These dark matter halos influence the rotation speeds of galaxies and play a crucial role in maintaining the stability of galaxies as they evolve. The future of galaxies is shaped by the forces at play in the universe. As the universe continues to expand, galaxies are slowly moving further apart. However, the gravitational attraction between galaxies can cause them to interact and merge, leading to the creation of new structures. The Milky Way, for example, is on a collision course with the Andromeda Galaxy, a process that will unfold over the next 4 billion years. When these two galaxies collide, they will merge into a single, larger galaxy. This merger will dramatically change the structure of both galaxies. The spiral arms of the Milky Way will be disrupted, and new stars will form in the aftermath of the collision. Over time, the merged galaxy will likely settle into a large elliptical galaxy, with a central supermassive black hole at its core. While this event is still far in the future, it highlights the ever-changing nature of galaxies and the forces that drive their evolution. In the distant future, as galaxies continue to evolve, they will eventually be isolated from one another as the expansion of the universe accelerates. As galaxies drift apart, star formation will slow, and the universe will become increasingly dark. Over billions of years, galaxies will fade, their stars burning out and their black holes growing ever more dominant. The fate of galaxies, much like the stars within them, will ultimately be shaped by the forces of gravity, dark matter, and time. Just as galaxies evolve and merge, so too does our understanding of them. Every galaxy, from the smallest irregular galaxy to the largest elliptical behemoth, carries with it the story of creation, transformation, and the eternal dance of the cosmos. As we continue to explore and study these magnificent structures, we gain new insights into the universe's past, present, and future. Gravity, the force that shapes the universe, is not only a fundamental force responsible for the motion of stars and planets, but also the architect of the cosmos. It is the invisible sculptor, molding galaxies, creating stars, and controlling the fate of celestial bodies across time. Yet, it is in the backdrop of an expanding universe that gravity finds itself locked in an eternal battle, one that will ultimately determine the future of the cosmos. This cosmic struggle between the forces of gravity and the accelerating expansion of space, driven by dark energy, plays a critical role in the universe's future. At its core, gravity is a force of attraction. Its influence permeates the entire universe, from the smallest particles to the largest galaxies. Despite being the weakest of the 4 fundamental forces, its reach is infinite, and its effects are magnified at the scale of planets, stars, and galaxies. Gravity holds everything together, keeping the planets in orbit around the sun, shaping the structure of galaxies, and preventing the universe from falling apart. Without gravity, the universe would lack the coherence and order necessary for the formation of stars, planets, and life. In the early universe, gravity played a crucial role in the formation of galaxies and cosmic structures. As dark matter coalesced, it acted as a scaffold, and gravity began to pull regular matter, gas, and dust into ever denser clumps. This process led to the birth of the first stars and galaxies. Gravity ensured that these cosmic entities remained bound together, giving rise to the grand structures we observe today. The universe, however, has not always expanded at the same rate. Gravity's influence has slowly weakened as the universe has expanded, leading to new and surprising phenomena. As the universe continues to expand, gravity is constantly pulling matter together, while the mysterious force known as dark energy is pushing it apart. Dark energy, which accounts for roughly 68% of the universe's energy, is a force that accelerates the expansion of space. It is often described as the anti-gravity force, pushing galaxies, stars, and even clusters of galaxies further apart. The exact nature of dark energy remains one of the greatest mysteries in modern science. but its influence is undeniable. Since the discovery of the universe's accelerating expansion in the late 1990 seconds, astronomers have come to realize that the universe is not only expanding, but doing so at an ever-increasing rate. This discovery reshaped our understanding of the universe's future, with dark energy playing a key role in shaping the ultimate fate of everything within it. At the same time, gravity, which was once the dominant force, now finds itself in a struggle against dark energy. For much of the universe's history, gravity was able to slow the expansion, pulling galaxies, stars, and clusters of galaxies together. However, as the universe expanded and dark energy began to assert its influence, gravity was gradually overpowered. The result is an accelerating universe, a cosmos that grows ever larger and emptier over time. Gravity not only shapes the structure of galaxies, but also determines their future. The balance between gravitational attraction and the forces that drive cosmic expansion has a profound effect on the fate of individual galaxies. Galaxies, like our own Milky Way, are in constant motion, interacting with one another through gravitational forces. As the universe expands, galaxies are moving away from each other, with distant galaxies receding faster than those nearby. This is a direct result of the expansion of space itself, driven by dark energy. However, the universe's expansion doesn't mean galaxies are isolated from one another. The force of gravity can still bring galaxies together, often in spectacular collisions. The most well-known example is the eventual collision between the Milky Way and the Andromeda Galaxy. While this event is billions of years away, it serves as a reminder of the complex interplay between the forces that shape galaxies. As these galaxies approach one another, their gravitational forces will begin to dominate, eventually merging into a single, larger galaxy. This process, known as a galactic merger, will significantly alter the structure of both galaxies, transforming them in ways we can only begin to imagine. Despite the vast distances between galaxies, gravitational attraction ensures that no galaxy is truly alone. Over time, as the universe continues to expand, galaxies will collide and merge, their stars and gas pulled together by the inexorable force of gravity. These interactions will create new structures, new stars, and possibly new systems that we cannot yet foresee. In this way, gravity continues to be the architect of cosmic evolution, even as the universe itself grows more distant and fragmented. Although the universe is expanding, galaxies are still bound together by gravity. This is largely thanks to the presence of dark matter, an invisible and mysterious substance that makes up roughly 25% of the universe's mass. Dark matter does not interact with light, which is why it remains undetectable by our telescopes. However, its gravitational influence is felt throughout the universe. Dark matter plays a critical role in the stability of galaxies. Without it, the gravitational forces within galaxies would be too weak to prevent them from flying apart. The presence of dark matter provides the extra gravitational pull necessary to keep galaxies intact, especially in regions far from their centers. It forms what is known as the dark matter halo, a vast, invisible structure that surrounds galaxies. This halo provides the additional gravitational force needed to maintain the structure of the galaxy, preventing it from losing its cohesion as the universe expands. Furthermore, dark matter is crucial in the formation of the cosmic web, a vast network of interconnected filaments that stretches across the universe. These filaments, made up of dark matter, act as scaffolds, guiding the formation of galaxies and clusters of galaxies. The interactions between dark matter and regular matter are fundamental to the large-scale structure of the universe. They allow galaxies to form, merge, and evolve in ways that are still not fully understood. As the universe ages, the tension between gravity and dark energy will continue to shape its destiny. Currently, Dark energy appears to be the dominant force, pushing galaxies further apart with every passing moment. However, this balance may shift over time, depending on the exact properties of dark energy. If dark energy continues to overpower gravity, the universe will continue to expand at an accelerating rate, ultimately leading to a state where galaxies are so far apart that they can no longer interact with one another. In this scenario, the universe would become increasingly isolated, with galaxies, stars, and planets drifting into the vast emptiness of space. Over time, stars will burn out, and galaxies will grow dim as star formation slows. The universe will slowly fade into darkness, becoming a cold, lifeless expanse. On the other hand, if gravity were to regain dominance, the universe would eventually slow its expansion, and the cosmic web of galaxies would begin to collapse. This process, known as the Big Crunch, would see galaxies, stars, and all matter being pulled back into a singular point, possibly leading to another Big Bang. This scenario is still a possibility, but current observations suggest that the force of dark energy is too strong for gravity to reverse the expansion. The ultimate fate of the universe remains uncertain, and scientists are still working to understand the underlying properties of dark energy and gravity. As we continue to observe and explore the cosmos, our understanding of these fundamental forces will deepen, providing us with a clearer picture of what lies ahead for our universe. Whether the universe expands forever or eventually collapses, it is clear that the forces of gravity and dark energy will continue to shape its future, guiding the cosmic dance for billions of years to come. The universe, in all its vastness, is not eternal in the way we often imagine. It is undergoing a quiet transformation, a gradual fading, not unlike the twilight of a day that slowly gives way to night. At the heart of this transformation lies the aging of stars. They are the lifeblood of the cosmos, lighting up the heavens and giving rise to elements that sustain life as we know it. However, stars, like all things, have a finite existence. Their death signals a shift in the universe's landscape, one that moves us toward a future that will, eventually, be defined by dimming lights and the slow cooling of cosmic matter. In the grand timeline of the universe, we are living in what is known as the stelliferous era, or the Age of Stars. This era, which began after the Big Bang and continues today, is defined by the formation and evolution of stars. It is a period of great creativity, where stars are born, shine brightly, and give rise to the elements essential for life. Stars form from the remnants of gas and dust in interstellar space, igniting nuclear fusion in their cores to create light and heat. However, this process of stellar birth and death cannot last forever. As stars age, they change, just as we do. The most massive stars burn through their nuclear fuel quickly, living short, explosive lives before collapsing into either supernovae or black holes. Smaller stars, like our Sun, burn more slowly and live much longer, but even they will eventually exhaust their nuclear fuel, causing them to swell up into red giants before ultimately shedding their outer layers and leaving behind a white dwarf. But it's not just the stars themselves that change the universe. As these stars age and die, they release heavy elements into the surrounding space, enriching the interstellar medium and providing the raw material for the formation of new stars, planets, and even life. This process of stellar death and rebirth is what gives the universe its dynamic character. However, as stars burn out and cease to form, the universe will begin to change in a way we have yet to fully understand. The most noticeable sign of the universe's aging is the gradual dimming of the stars themselves. As the universe expands, the rate of star formation is slowing down. This is due, in part, to the depletion of the raw materials necessary to form new stars. Gas clouds are being used up, and the birth rate of new stars is in decline. Meanwhile, the stars that are already in place are aging and becoming less luminous. The death of stars, particularly the most massive ones, contributes to this dimming. When a star reaches the end of its life cycle, it will either collapse into a white dwarf, explode in a supernova, or form a black hole, depending on its mass. These dead stars will no longer contribute light to the universe, leaving behind cold remnants. The once vibrant sky will slowly fade, with fewer stars shining brightly. As star formation declines and older stars fade away, the universe will move toward a more subdued, more somber state. One of the key indicators of the aging universe is the redshift. As the universe continues to expand, the light emitted by distant stars and galaxies is stretched, causing it to shift toward the red end of the spectrum. This phenomenon, known as cosmological redshift, is not just a sign of the expanding universe, but also a reflection of the dimming of the cosmic light. The further away an object is, the more its light is stretched, resulting in a deeper red color. Over time, the stars that once shone brightly will be dimmed by the expanding space itself. This redshift is not limited to just the light we receive from distant stars. It is also an indication that the universe's expansion is accelerating, a realization that has profound implications for the future of the cosmos. As the universe expands, light from distant stars will become even more redshifted, and these stars will eventually fade from our view. In this way, the redshift serves as a quiet reminder of the inevitable aging process the universe is undergoing. While the universe's slow fade is visible in distant galaxies, we can observe the aging process of stars much more closely in our own cosmic neighborhood. Our Sun, for example, is currently in its middle age, burning through its supply of hydrogen and slowly transforming into a red giant. In about 5 billion years, the Sun will expand, swallowing the inner planets, including Mercury, Venus, and possibly Earth. As the Sun swells, it will become a pale, swollen ball of gas, its luminosity increasing dramatically before it sheds its outer layers and settles into its final stage, a white dwarf. The expansion of the Sun is just one example of how stars age. The transformation of a star into a red giant marks a significant shift in the cosmos. For many stars, this phase is followed by the end of their lives. As the Sun nears the end of its red giant phase, it will begin to expel its outer layers, leaving behind a dense core of carbon and oxygen. This white dwarf will slowly cool and fade, eventually becoming a cold, dark remnant. This is a fate shared by many stars, though the more massive stars will meet a more violent end in a supernova explosion, leaving behind a black hole or a neutron star. As stars age and their characteristics change, so too does the overall color of the universe. The early universe was full of hot, blue stars, massive stars that burn brightly and quickly. But as time passes, these stars burn through their fuel and give way to older, redder stars, red dwarfs, which are cooler and dimmer than their blue and yellow counterparts, will come to dominate the universe in the future. These stars burn their fuel slowly, with lifespans that stretch across trillions of years. While red dwarfs are long-lived, they are not the bright beacons we associate with the stars of our current sky. They are faint, distant, and invisible to the naked eye. This shift from blue to red is symbolic of the universe's aging process. The vibrant, youthful era of star formation will eventually be replaced by a quiet, subdued universe. Stars will burn more slowly, and the cosmic light will fade. The night sky, once filled with the bright flashes of newborn stars, will slowly grow darker. As red dwarfs become the dominant form of stellar life, They will mark the end of the stellar era, and the universe will begin to settle into its twilight years. As the universe continues to expand, star formation will continue to slow. The gas clouds that once gave rise to new stars are being used up, and the conditions necessary for star formation will eventually be exhausted. Over the next few billion years, new stars will be born less frequently, and the last new star will eventually form. After that, the universe will enter a period known as the degenerate era. In this era, the universe will consist mostly of white dwarfs, neutron stars, and black holes, remnants of stars that have already burned out, with no new stars to light the way. The universe will become an increasingly cold and dark place. The process of star formation will cease, and the remnants of old stars will drift through space, slowly cooling and fading into nothingness. The degenerate era is a time of cosmic stillness. There will be no more brilliant supernovae, no more nebulae glowing with the birth of new stars. Instead, the universe will be populated by the faint, slowly fading remnants of its former glory. The lights of the universe will go out, one by one, leaving behind a cold, silent expanse. Even as the stars burn out and the universe moves toward its quiet end, there are some who believe that life, or at least consciousness, could survive in some form long after the stars are gone. Some scientists speculate that highly advanced civilizations could find ways to adapt to the dying universe, harnessing energy from black holes or manipulating the very fabric of space-time itself. In this final chapter of the universe's story, perhaps the most profound question is not about the death of stars, but about the survival of life and intelligence. Could civilizations find a way to survive the cosmic dusk? Could consciousness persist in the darkness, long after the stars are gone? These are questions we can only speculate on, but they add a final layer of mystery to the universe's long journey toward its quiet end. As the universe ages and the stars fade away, the cosmos will enter a new chapter, one that is defined not by the brightness of stars, but by the slow cooling of its matter. It will be a time of stillness, a time when the light of life will flicker faintly before being extinguished altogether. Yet, even in this fading, there is beauty, an enduring reminder that even in the darkest of nights, the light once shone brilliantly, and the universe once danced in the glow of stars. The universe, in all its grandeur, is not infinite in the way we often imagine. It's not an eternal fire that will blaze forever, casting light into the farthest reaches of space. Instead, it is more like a candle burning down, its light dimming and eventually extinguishing in an endless silence. The end of the universe is not a violent clash or a grand finale, but rather a slow, quiet, inevitable fading, a heat death. This concept, though unsettling, is grounded in the very laws of physics that govern the cosmos. It is the culmination of an irreversible process called entropy, the tendency of energy to disperse and move toward a state of uniformity and stillness. Understanding heat death requires not only an exploration of the universe's gradual cooling, but also a meditation on the ultimate fate of all matter, energy, and even time itself. Entropy is a force that acts like a slow tide, wearing down everything it touches. It's the reason why your cup of hot coffee cools down over time, why the wind erodes mountains, and why the stars burn out after millions or billions of years. It's the universal force of disorder. And just as entropy increases in the small, it does so in the grandest scales. Too, every star, every galaxy, every cosmic body is slowly losing its energy, moving toward a state of perfect balance where no more work can be done. This is the ultimate expression of entropy, heat death. The laws of thermodynamics tell us that in an isolated system, the total entropy will always increase. The universe, as an isolated system, is no exception. As the stars burn through their fuel and collapse into white dwarfs, neutron stars, or black holes, they release their energy into the surrounding space. Over time, however, this energy becomes more and more dispersed, and the temperature of the universe falls, inch by inch, toward absolute zero. The universe will be bathed in a faint, diffuse glow, nothing more than the afterglow of all that has passed. At the peak of this process, the universe will reach a state where all energy is evenly distributed, and no physical processes can occur. Stars will no longer shine, and galaxies will cease their rotations. Space will become an empty void, as every particle has reached the same energy state. This is the universe's final, silent equilibrium, the heat death. The final stage of the universe's life is a time of cosmic decay. Stars will burn through their nuclear fuel, reaching the end of their lives in one of three ways: as a white dwarf, a neutron star, or a black hole. But these are not permanent fixtures. They too will eventually burn out. A white dwarf, for example, may remain hot for billions of years, but it will eventually cool down, losing its light, until it is indistinguishable from the surrounding space. A neutron star, the remnant of a supernova explosion, will continue to radiate energy for a long time, but it, too, will eventually fade into nothingness. The black holes, once the most mysterious and powerful objects in the universe, will also play a part in this cosmic end. While they may seem to persist, holding on to matter and light in their singularity, they too are subject to entropy. This is where the theory of Hawking radiation comes into play. Proposed by physicist Stephen Hawking in 1974, it suggests that black holes can emit radiation, eventually leading them to lose mass and energy over time. This process is incredibly slow, but it means that even the most massive black holes will eventually evaporate. However, the timescale for this is staggeringly long, on the order of billions or even trillions of years. The largest black holes will take longer to vanish than the current age of the universe itself, but eventually, even they will fade, leaving behind an empty, dark cosmos, void of light and energy. As black holes evaporate and stars die, the universe's brilliance will grow fainter, slipping into the darkness of oblivion. Once the last star has extinguished and the black holes have evaporated, the universe will be a cold, lifeless expanse. This is the ultimate state of heat death, without any energy sources to drive processes. All activity will cease. The universe will be a still, dark place, populated only by isolated particles drifting aimlessly through the vast emptiness. In this final state, the temperature of the universe will approach absolute zero. There will be no more radiation, no more stars, and no more life. Even the most fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces will have diminished to the point where no meaningful interactions occur. The universe will be frozen in time, a dark and lifeless void, with no possibility for renewal. As entropy reaches its maximum, no more work can be done. There will be no temperature differences, no energy to sustain life, no stars to illuminate the dark corners of the universe. The future will be one of quiet isolation, as all things slowly lose their energy and fade into the infinite silence of space. While heat death is the most widely accepted end to the universe, it is not the only possibility. The beauty of science lies in its openness to new ideas, and several other theories exist about how the universe might end. One of the most intriguing possibilities is the Big Rip, a scenario in which the expansion of the universe accelerates to such a degree that it tears apart galaxies, stars, planets, and even atoms themselves. The Big Rip arises from the concept of dark energy, a mysterious force driving the accelerated expansion of the universe. If dark energy continues to increase in strength, it could overcome the forces of gravity and push all cosmic structures apart, eventually ripping apart the very fabric of space-time. In this scenario, the universe would end, not in a slow fade, but in a violent stretching of reality itself. Another theory, known as false vacuum decay, suggests that the universe could transition to a lower energy state, radically altering the laws of physics as we know them. This catastrophic event would have the power to erase the current structure of the universe and replace it with something entirely different, fundamentally rewriting the rules of existence. Though these theories are fascinating, they are speculative at best, and the heat death remains the most plausible end given our current understanding of the cosmos. But these alternate theories serve as a reminder of how little we know about the true fate of the universe, and how much more there is to explore. The concept of heat death is more than just a scientific theory. It invites deep philosophical contemplation about the nature of existence itself. The idea that everything, even the stars, must come to an end challenges our notions of immortality and the significance of life in the grand scheme of things. If the universe, as we know it, is destined to end in a cold, dark void, what does that say about the purpose of life and the fleeting moments we experience? Some may find this perspective sobering, even unsettling. The thought of a universe that will one day become lifeless and still can feel like an existential weight. However, there is beauty in the understanding that the universe has a beginning, a middle, and an end. Its life cycle mirrors our own in many ways, from birth to death, with all the richness in between. The inevitability of heat death can inspire us to appreciate the present moment, to savor the warmth and light of the stars while we have it. Ultimately, the idea of heat death challenges us to think about our place in the cosmos. It reminds us that we are part of something much larger than ourselves, a universe that is in constant flux. And while it may end in a final, eternal stillness, the journey to that point is filled with incredible complexity, beauty, and mystery. The stars may fade, but the memories of their brilliance will remain etched in the fabric of time. As we drift further into the heart of the universe's mysterious future, we arrive at its most enigmatic and awe-inspiring objects, the black holes. These cosmic behemoths, with their immense gravity, are the ultimate destroyers and creators of the universe, reshaping both the fabric of space and time itself. But even the mighty black hole is not immune to the relentless forces of entropy. When the universe has exhausted all its stars, and their once brilliant light has faded away, black holes will remain as the final remnants of the cosmos. Yet, their story does not end in eternal darkness. They, too, are bound by the laws of physics, which, despite their power, dictate an inevitable fate. Black holes, for all their mystery, are not purely fictional objects of science fiction. They are real, and their presence is confirmed by extensive astronomical observations. A black hole forms when a massive star exhausts its nuclear fuel and its core collapses under its own gravity, creating a singularity, a point in space where gravity is so strong that not even light can escape it. Surrounding the singularity is the event horizon, a boundary beyond which nothing can return. The peculiar nature of black holes arises from their ability to warp space and time to an extraordinary degree. Inside the event horizon, space itself becomes so curved that all paths lead inward, toward the singularity. Time itself slows down as you approach the event horizon. For a distant observer, watching an object fall into a black hole would seem like time is stretching endlessly, the object becoming frozen at the horizon. Yet, for the object falling in, time would proceed normally. But the experience of crossing the event horizon would be a one-way trip. an irreversible plunge into the void. Black holes have long been thought of as ultimate cosmic prisons, where matter is trapped and lost forever. However, in 1974, physicist Stephen Hawking proposed a revolutionary idea that changed our understanding of black holes forever. The concept of Hawking radiation, Hawking's theory, based on the principles of quantum mechanics, suggested that black holes are not entirely black. Instead, they emit radiation due to quantum effects near the event horizon. This radiation arises from pairs of virtual particles that spontaneously pop in and out of existence just outside the event horizon. One of these particles can fall into the black hole, while the other escapes into space. The escaping particle is what we observe as Hawking radiation. This radiation has profound implications. If a black hole emits radiation, it loses energy, and over time, this loss could cause the black hole to shrink. The process would take an incredibly long time, but it means that black holes are not permanent. Eventually, they will evaporate completely, leaving behind only the faint glow of Hawking radiation. The larger the black hole, the longer this process takes. For instance, a black hole with the mass of our Sun would take approximately 1067 years to evaporate. But in the end, even the most massive black holes will vanish, leaving a void in their wake. As the universe's stars burn out and their energy dissipates, black holes will become the dominant objects in the cosmos. They will be the last bastion of gravity, pulling everything into their depths. But as time progresses, even these titanic entities will succumb to the slow march of entropy. During the black hole era, the universe will be a place of stillness. The galaxies, once bustling with activity, will have long since merged into large, empty voids. The remaining black holes will be the only structures capable of exerting any significant force. But as they continue to evaporate, the universe will grow colder, darker, and emptier. During this time, only the faintest traces of cosmic activity will remain. As the black holes evaporate through Hawking radiation, they will slowly lose mass, their singularities shrinking over time. The last moments of these stellar remnants will be marked by a final burst of energy, a sudden explosion of radiation that will leave the universe in an even more profound silence. In the end, the universe will be populated only by isolated particles, wandering through an infinite and empty space. The black holes, the last vestiges of a once vibrant cosmos, will have faded into nothingness, leaving no trace of the universe's former glory. One of the most profound questions raised by the existence of black holes is the so-called information paradox. According to the laws of quantum mechanics, information cannot be lost. It must be preserved in some form, but black holes, as we understand them, seem to contradict this principle. When matter falls into a black hole, it seems to be completely destroyed. The information about the state of that matter, including its position and velocity, appears to be lost forever. However, this presents a fundamental conflict with the laws of quantum mechanics, which assert that information is never truly lost. In recent years, physicists have proposed various solutions to this paradox. One of the most interesting ideas is the holographic principle, which suggests that all the information that falls into a black hole is actually stored on its event horizon, encoded in a way that is not immediately apparent to us. This would mean that, despite appearing to lose information, the universe still preserves it in a different form. Other proposals suggest that the information could be released back into the universe through Hawking radiation. However, this radiation is highly scrambled and chaotic, making it nearly impossible to reconstruct the original information. Ultimately, the resolution of the information paradox remains one of the greatest mysteries in modern physics. It represents a fundamental conflict between the principles of quantum mechanics and our understanding of space and time. The answer to this question may be key to unlocking the ultimate fate of the universe, and it is a puzzle that continues to perplex scientists. As the universe drifts toward its final days, time itself becomes increasingly irrelevant. Once the black holes have evaporated and all matter has been scattered across an ever-expanding universe, space-time will lose its meaning. The very fabric of reality, as we understand it, will cease to exist. With the disappearance of black holes and the final vestiges of matter, the universe will enter a state of perfect equilibrium. There will be no energy differences, no temperature gradients, no activity. The universe will exist in a state of timeless stasis. At this point, there will be no events to mark the passage of time. The universe will be a cold, dark, and empty place, devoid of life, energy, and movement. It will be as if the very concept of time has come to an end, leaving behind only the faintest echoes of the cosmos that once was. The ultimate fate of the universe is both humbling and awe-inspiring. From the birth of stars to the slow decay of black holes, the universe's journey is one of constant change and transformation. Yet, in the grand scheme of things, everything eventually succumbs to the same force entropy. It is a reminder that nothing lasts forever, and even the most massive, enduring structures will eventually fade into the void. As we contemplate the end of the universe, we are reminded of our own fleeting existence. In the vastness of space and time, our lives are but a brief flicker, but that flicker is meaningful. In the short time that we have, we can appreciate the beauty and wonder of the universe, understanding that, though it may fade, the memories of its brilliance will endure in the minds of those who witnessed it. The cosmos may come to an end, but the legacy of its existence will never be truly erased. As the cosmos reaches the end of its life cycle, and we peer into the distant, unimaginable future, we are confronted with a profound question that has haunted humanity for centuries. What comes next? We've explored the path that brought us here, from the Big Bang to the vastness of space we see today, and we've witnessed the inevitable conclusion, entropy's quiet triumph, the slow death of stars, and the ultimate dissolution of black holes. But even as we approach the end of this cosmic journey, there remains a question that seems to echo through time and space. Can life, consciousness, or perhaps something else, to survive in this dying universe? What if the universe isn't truly finished? Is it possible that there are ways to prolong its existence, or even create something entirely new from its ashes? The future, in all its uncertainty, remains an open question, a challenge not just for physicists and cosmologists, but for every curious mind that gazes at the stars and wonders what will come of it all. In the twilight years of the universe, with stars flickering out and the expansion of space accelerating, it may seem that life, as we know it, would be impossible to sustain. But that doesn't mean that the universe will be devoid of existence altogether. In fact, the end of stars could mark the beginning of a new era, one in which advanced civilizations, equipped with unimaginable technologies, might still find ways to thrive. The death of stars signals the eventual depletion of usable energy for life. Yet, as any advanced civilization might strive for, the ingenuity of technology could offer them a solution. This idea isn't far-fetched, in fact. It echoes in some of the most ambitious proposals of theoretical physics and engineering. Could we manipulate energy sources in such a way that life could endure long after the last star dies? Could we unlock new forms of energy from the dark corners of the universe itself? One such possibility arises from the concept of star, lifting a hypothetical method in which advanced civilizations would harvest material from dying stars to prolong their life. By extracting energy and matter from stars before they collapse, or even by slowing down their natural decay, such civilizations might extend the life of the stars or create entirely new, artificial sources of energy that don't rely on the death of stars. This concept is bound by the limits of technology Yet, it sparks a fascinating thought. Could civilizations outlive the physical universe by manipulating cosmic forces? But perhaps it's not just the stars that offer a potential lifeline. What if the most mysterious and destructive objects in the universe, black holes, could be used as a resource? The very objects that devour everything, even light, may hold the key to a new form of energy. It's a radical concept, but the idea of black hole energy harvesting isn't as far out as it might first appear. One proposed method for extracting energy from black holes is through Penrose processes, a phenomenon that allows for the extraction of energy from a rotating black hole. As a black hole spins, it creates a vast amount of energy in the form of rotational energy. By sending matter into the black hole's ergosphere, the region just outside the event horizon, it might be possible to extract energy and convert it into usable forms. This idea, still theoretical, could offer advanced civilizations the means to survive long after the last stars have burned out. While harvesting energy from black holes is still purely speculative, it opens the door to a thrilling thought even in the death of stars. There might be a way to harness cosmic forces to sustain life. As the universe ages and its resources dwindle, the most unlikely of sources, black holes, could emerge as a final lifeline for those who can master their power. One of the most mind-boggling possibilities that arises when we think about the far future of our universe is the notion of the multiverse. If the universe is bound to reach a final, entropic state, a state where nothing new can form, and all energy is evenly dispersed, then what if there is more? What if our universe is only one of many? The idea of the multiverse proposes that there are multiple, perhaps infinite, universes, each with its own set of physical laws, constants, and dimensions. In this scenario, as one universe approaches its final days, another might be born. This could take the form of a baby universe, a new cosmos that begins with its own Big Bang, perpetuating a cycle of creation and destruction, birth and death. This theory suggests that the end of one universe could simply lead to the birth of another, much like the constant rebirth of stars. If the multiverse is real, there could be endless opportunities for life to continue, not necessarily within our own universe, but across many. However, this remains highly speculative and is grounded in theoretical physics. For now, it's a tantalizing glimpse into the possibility that the death of one universe doesn't have to mean the death of existence altogether. Instead, it could signal the beginning of a new, unknown reality. As the universe drifts into entropy, and as all matter fades away into the cold, dark void, there's another peculiar and unsettling possibility: the emergence of Boltzmann brains. In a universe approaching maximum entropy, random fluctuations might create isolated pockets of low entropy structures. These structures, by sheer chance, could give rise to consciousness. In this scenario, a Boltzmann brain would be a random collection of particles that forms for just a fleeting moment in time, long enough to become self-aware. This consciousness would be an illusion, a brief flash of awareness in the void, with no surrounding matter or lasting structure. While the notion of Boltzmann brains might seem far-fetched, it raises profound questions about the nature of consciousness and existence. Could there be a version of consciousness that exists without a physical body, existing only as a brief flash of thought in a decaying universe? The concept of Boltzmann brains challenges our very understanding of life and consciousness. It's a reminder that, in a universe without stars or planets, consciousness itself might find a way to emerge in unexpected, transient forms. As we approach the end of time, the final days of the universe, the eventual death of the last black hole, we are left with one final, deep question. What is the meaning of it all? When stars die, when galaxies collapse, and when all matter has dissipated into the void, does it all just end? Or is there something more to existence than the mere mechanics of the universe? It's a question that has plagued philosophers and scientists alike for centuries. And as we contemplate the vastness of time, space, and the eventual collapse of everything, we are left to wonder about our place in it all. Perhaps the true meaning of existence isn't found in our ability to survive or conquer the cosmos. Perhaps it's in the beauty of the fleeting moments, the brief flashes of awareness, the fleeting interactions, the connections we form with the universe in our short time here. As the universe slowly moves toward its distant future, the question of existence still has no final answer. Our time within this vast cosmos is brief. Yet, it is within these fleeting moments that meaning is found not in an eternal universe, but in the curiosity, understanding, and awe we gather along the way. Even if the universe one day fades, the discoveries we make, the beauty we witness, and the stories we uncover will continue to resonate far beyond us. If you're drawn to the mysteries of space and the quiet wonder of the cosmos, subscribe and turn on notifications to join us. Together, we'll keep exploring the universe, one gentle journey at a time.